Mike. We're at 52, coming back down 51 RPM.
Roger, we copy. You guys look good.
Brian, you should show the spacecraft on internal power now.
Roger, we saw that.
5, 4, 3, 2, 1, go. Beautiful.
This is the high bay area of Hughes Aircraft Company's satellite assembly facility. The communication satellites manufactured by Hughes since the early 1960s have provided more than 250 years of service in space. The day these pictures were taken, a group of astronauts was visiting the facility in preparation for yet another pioneering step in space communications. The launch of 2 communication satellites, the first commercial payload carried by the Space Shuttle. The 2 satellites, both built by Hughes, were the SBS, third in a series of satellite business system satellites, and Anik-C, the 5th in a series of Canadian communication satellites. The satellites were carried into space in November of 1982. After reaching orbit, the shuttle maneuvered to launch the first satellite. Approaching the time for ejection, the sun shield was opened. The shuttle crew then initiated spin-up of the satellite, providing the necessary stability when it would leave the shuttle. One last checkout, then deployment. After coasting halfway around the Earth to the dark side, the satellite fired its perigee kick motor. The 1.5-minute burn moved the satellite into an elliptical transfer orbit. After burnout, the expended motor was jettisoned. Then the satellite turned to the position required for later firing of its apogee kick motor. Later in the mission, the second satellite was deployed. Its rocket motor was fired, pushing it into an elliptical transfer orbit. Each satellite then went through the following procedures. At the peak of the elliptical orbit, a second motor was fired, propelling the satellite into a nearly circular geostationary orbit 22,300 miles or 36,000 kilometers above the equator, directly south of the United States. At this altitude, its speed exactly matched the rotation of the Earth. Thus, the satellite remained stationed above the same spot. The spacecraft was again turned, this time to its operational position. Its antenna platform was then despun, the communication dish antenna raised, and the telescoping solar panel extended to expose the full complement of solar cells to sunlight. The satellite was now more than 20 feet tall. Today, high in geostationary orbit, the Satellite Business System spacecraft provides communications to businesses and other organizations throughout the United States, and Anik-C provides voice, video, and data communications throughout Canada. But launching the first 2 commercial satellites from the Space Shuttle was only one more achievement in a long history of Hughes successes with geostationary satellites. A success story that began more than 20 years ago with the launch of Syncom, the world's first synchronous orbit telecommunications satellite. Those first Syncoms were not large by today's standards, having only 1 television channel or 50 telephone circuits. But in those days, they were giants. On the 26th of July, 1963, Syncom was successfully placed in a geostationary orbit above the Atlantic Ocean. A year later, another Syncom was launched into orbit, this time over the Pacific. It was this Syncom that relayed pictures of the 1964 Olympics from Japan to the world. But another momentous event had already taken place. 19 nations of the world organized an international consortium called Intelsat, whose purpose was to develop a privately owned communication system using geostationary satellites. The Comstar Corporation, representing the United States, became manager of the system. The group's first satellite was purchased from Hughes and named Intelsat I, but became better known as Early Bird. Nearly double the power of Syncom, Intelsat I provided one television channel or 240 telephone circuits. In 1967, a new Intelsat series of satellites was placed in orbit for the consortium, which by then had grown to more than 50 nations. Called Intelsat II, the new satellites led to the first global telecommunications network, which brought the entire world historic events as they happened. Meanwhile, the engineers and scientists at Hughes were extending satellite technology to new frontiers. ATS, Applications Technology Satellites, were designed for NASA to conduct scientific experiments using geostationary satellites, including experiments for improving communications between planes in flight and ships at sea. TACSat I was then developed for the U.S. Air Force. With nearly 1,000 watts of solar energy and a capacity of 10,000 simultaneous telephone conversations, TACSat proved the feasibility of using geostationary satellites for tactical communications. In the early 1970s, Hughes created a series of 8 new satellites for the Intelsat consortium, which had grown to more than 80 nations. Called Intelsat IV, each could handle any combination of 6,000 telephone conversations or 12 simultaneous color TV channels, as well as facsimile and data. By 1973, the Intelsat organization required even greater global communications. To meet this need, Hughes developed the Intelsat IVA series. These employed a unique spot beam concept, which effectively doubled the capacity over the Intelsat IV series without a corresponding increase in size. At this time, Hughes pioneered the development of national communication satellites by inventing a technique that focused a geostationary satellite's beam within the borders of a single country. The first of these satellites was a series of 3 named Anik, developed for Canada. In 1974, Hughes created the Westar program for Western Union. Each Westar antenna was focused to cover the entire United States, providing border-to-border commercial communications. At about the same time, 4 satellites called Comstar were developed for the Comsat General Corporation and American Telephone and Telegraph, each with a capacity of 18,000 high-quality voice circuits. This large capacity was achieved by a cross-polarization technique, which permits reuse of the same frequencies without separating the beams. In 1976, a 2-satellite system called Palapa was created to bring television and telephone service to the many islands of Indonesia. A short time later, the Marisat series was developed to provide rapid and reliable telecommunications for the U.S. Navy and the National Maritime Service. During the late 1970s, it became apparent that custom-built satellites were becoming far too costly. So Hughes developed a basic spacecraft known as HS-376 that could be launched either by rocket or by space shuttle, and which could be adapted to a wide variety of customer requirements. Telecommunications capacity and satellite lifespan were significantly increased. And through the use of a telescoping solar panel, the electrical power was doubled. 27 HS-376 model spacecraft have been built or are on order for 9 different customers in 6 different countries, including the Anik-C and SBS-3 launched by the Space Shuttle. Each satellite is capable of transmitting messages directly to each customer's own antenna, some of which Hughes also manufactures and installs. In preparation for the deployment of the Indonesian and Canadian satellites, the crew of Shuttle number 7 paid a visit to Hughes. The crew, which included America's first female astronaut, was able to witness checkout of both satellites, as well as talk to the Hughes satellite experts. Hughes is also developing a series of wide-body telecommunications satellites called LESAT. These are designed for launch from the Space Shuttle exclusively, allowing an increase in diameter from 12 to 14 feet. These spacecraft will be owned by Hughes Communication Services Incorporated, which will lease their services, hence the name LESAT. 4 of these will be used by the Department of Defense. In addition to telecommunications satellites, Hughes developed several special purpose satellites. For example, a unique series of weather satellites was developed for Japan's National Space Agency. Each of the satellites carries a special Hughes radiometer that produces both high-resolution visible light and infrared weather pictures, providing Japan with around-the-clock storm warnings. 2 of the satellites were launched in Japan by the Japanese. For the United States, Hughes produced a series of 6 weather satellites. The latest generation carries a new instrument that not only provides 2-dimensional pictures of the Earth's surface and cloud cover, but also measures atmospheric temperatures and moistures at various altitudes, providing a 3-dimensional weather profile. NASA's Landsat satellites, which examine Earth's resources from space, carry several Hughes instruments, including an advanced thematic mapper that provides pictures of such detail they look like photographs. Early in the 1980s, it became clear that the demand for global communications would exceed the capabilities of current Intelsat satellites. Consequently, the Intelsat consortium, now grown to more than 100 nations, awarded Hughes a contract to build a new generation of telecommunications satellites designated Intelsat VI, shown here, full size in this painting. Each Intelsat VI will carry 33,000 two-way telephone calls and 4 TV channels, which is more than double the capacity of current Intelsat satellites. These will be the most massive commercial satellites ever built, 39 feet tall and 12 feet in diameter. As we entered the decade of the 80s, more than 100 countries, territories, and possessions had full-time satellite communication services. And revolutionary changes in technology are still taking place. These new advancements, plus use of the Space Shuttle, will allow each new generation of satellites to achieve results undreamed of at the time of the first small Syncom. By pioneering these new concepts, Hughes will continue to be a leader in this expanding field, creating a new world in space through electronics.
Columbia, Houston, we've got a super shot of the payload coming out.